So Paris, we have about 1 minute left. So I just welcome everybody to our talk. Thank you very much for your trying to actually all the contributions. We will start from Professor Ghosh. So he's going to talk about his recent work. So now it's exactly 2:30. So Paris, Susan, you can start now, while we're still waiting for somebody coming. Yeah. Can, you can start now. Yeah, you can start now.
I can start?
Yeah.
Okay,
Yeah,
thank you.
Yeah.
Thank you so much. I'm extremely grateful to the organizer, especially Professor Enjong Wang, for giving me this opportunity to speak in this prestigious Marshall Brassman meeting. Right? So I'm honored to give this talk. As we know, this is really exciting time for black hole physics because of the numerous reason, which is evident from my home first slide. So Event Horizon Telescope has released the observation first image of the black hole, and the results are consistent with the Kerr black hole of general relativity. However, they didn't rule out any modified theory of gravity or any other object which also caused the photon sphere. So there is a scope for modified gravity. I'm sure there are many exciting questions will be addressed with the Event Horizon Telescope, and also there are, I'm sure there will be many exciting questions will be also asked. Now, in this paper, in this talk, we will be considering 4D AGB black hole as a M87 star, and we will investigate what is the constraint on the parameter space of the black hole. Right. So let me start with the level of gravity. The action of the level of gravity, which was given in the 71 by Lolog. However, it became popular only when the string theory found that the 4D EGB, 4D Einstein-Gauss-Bonnet action is the low limit of the heterotic string theory. So this is a general Lolog action, and first is the cosmological term L0, second is R, and the important contribution in the first Lovelock is the second order curvature term, which is a quadratic curvature term, and it is called Gauss-Bonnet. And the action for the Gauss-Bonnet, then we can simplify the above action to this. Now, this became very important, and the important is that the EGB works only in the higher dimension. This quadratic curvature is adjusted in such a way that the equation of motion is still second order, right? So that is where, and this is the most studied level of gravity is the Einstein-Gauss-Bonnet gravity. Now the problem is that it requires higher dimension. Yes, it requires higher dimension because in 4 dimension it is total derivative, and hence it doesn't contribute to the dynamics of the dynamics, right? Now, if we write the again Einstein-Gauss-Bonnet gravity, then you get following. This is the equation of motion you get on varying the Lagrange on varying the action, and we have two additional terms. One is we have additional term HAB, which is the Lancos tensor. Cosmological constant is there. So, but we will be considering cosmological constant as a 0. Now, first very important solution to the Einstein-Gauss-Bonnet gravity was given by Bulwer-Dazer, and which is a very famous solution, which has this form. Right. This was the first solution for the low energy heterotic string theory, that is Einstein-Gauss-Bonnet theory. Now, as I said, 4 dimension, it reduces to total derivative, hence does not contribute the field equation. So what happened was in 2019, this Galvan-Lin, 2020 rather, Galvan-Lin proposed made a Gauss-Bonnet coupling constant as alpha upon d minus 4. he made like this. And then if you vary the action, vary the LGB, then d minus 3 which d minus 4 which appears in the numerator goes away because of this singular transformation. Right now, when and at the field, this was done at the level of field equation, and it gives us solution of 4-dimensional black hole solution. This is the black hole solution. Very important that it bypasses a Lovelock theorem, and also it is free from the Ostrogoretsky instability. They also claim that they resolve the singularity problem, but that was in the controversy, which I'll come later. Now, because of this, there was researchers were given very lot of attention to this theory. Let me say a few words about this, then I'll come to my Gauss-Bonnet rotating black hole solution. So this is a solution which at small distance recovers the GR solution, which is Schwarzschild-Dirichlet negative branch. As we know, there are two branches of the solution, plus minus. The positive branch has the negative mass, so it is unphysical. But the important is at small distance, the gravitational force is repulsive. That's why they said they could resolve the singularity problem. However, this proposal was originally proposed by Tomozova, well back in 2011, right? So they have gravity with quantum correction, which gives exactly this solution, and they also showed that at short distance it is gravitationally repulsive. It is gravitational force is repulsive. But important is it is also solution of four-dimensional non-relativistic Horava-Lifshitz gravity, which was shown by these people. And also Professor Kai showed that in the semi-classical Einstein equation with conformal anomaly, the exactly same solution, but the charged version of this appear as a solution. So this was not old proposal, but after the proposal of Galvan-Lin, it attracted a lot of interest. As I said, they said the solution resolves the singularity problem. However, if you see this picture, there is a problem that the particle reaches singularity in finite time. This was the claim: gravitational force is repulsive at short distance, thus infalling particle never reaches. But these people have shown that the particle reach in the finite time the singularity, right? And therefore there is a curvature singularity. Although metric function is finite, but there is a curvature singularity. So that claim was refuted. The Galvan solution also attracted a lot of criticism, but however, we found that spherical symmetry, it is fine. When you consider spherical symmetry, it is fine. You take any method. There were various methods. After criticism, various methods were proposed for the 4D EGB solution. But all those methods give the exactly same solution as the Galvan-Lin solution. So this spherically symmetric solution is exactly fine But when you have departure from spherically symmetry, some people have shown there can be a problem. But anyway, we took the spherically symmetry of Galvan-Lin and applied modified Newman-Jennings algorithm to generate the rotating counterpart of that solution. Now, this modified Newman-Jennings was proposed by Mustafa. I didn't put the reference. Mustafa and et al. And we have proved in this paper this solution. They claim that this solution is satisfies the field equation. However, we didn't check. But mostly it happens that in modified theories of gravity, the rotating black hole solution has additional stresses. And it is true for all modified theory, rotating modified theory black hole solution obtained using Newman-Jennings algorithm. So this is a solution valid in all other theories, which I mentioned earlier: Horava-Lifshitz gravity, also semi-classical gravity, and gravity with quantum correction, and many other like dimension reduction of Kaluza-Klein. Right. So then we analyze the horizon standard definition, which is used in the curve, and for A is equal to 0, you have this horizon R, inner horizon R plus minus is equal to this. So you have chance of naked singularity also, but naked singularity was not dealt by us because the shadow cast by the naked singularity is very, very small, which is not consistent with the event horizon telescope. So we analyze this the horizon, you can see the green line correspond to the Kerr case. It is below green line is the Kerr case. So the horizon radius decreases. I have not shown the Kerr case here, but it is below. So horizon radius is decreasing, and for a given parameter, we can find an extremal value of alpha, for which if the value is greater, then you have no black hole or black hole with two horizon, Cauchy and event horizon. So this is the behavior of horizon. So because the horizon radius reduces, that's why shadow size will be also reduced. So that we'll see in the detail later. And we have also identified the static limit surface, because that is important and it has an influence on the outer blue line is the inner blue line is the event horizon, whereas outer red line is the static limit surface, and region between is called ergo region. And that has a effect. It is affected by the Gauss-Bonnet parameter, and that's why it has a consequence on the so-called time-lapse process as well as on the shadow of the black hole. So my main topic is the shadow of the black hole. So black hole embedded in optically thin emission region will produce an observer signature, namely shadow. Right? Basically, it is a strong gravitational lensed image of the image horizon or photon sphere. Right? Now we know that this concept of a black hole shadow was originally proposed by Bardeen and Sinch long ago in 70s. But imaging was possible only later in 2000 when the Pilecki proposed a VLBI technique, and then they have chances of imaging. So the imaging started about imaging theoretically they started in 2000, and then finally it was realized in 2017 and 19 they released the picture. So we need to consider motion of the photon. So this metric, like Kerr black hole, has is independent of T and phi. That's why it admits two Killing vector corresponding to two conserved quantities. And then you have additional conserved quantity Carter, the Carter constant. And Carter gave the idea to write the Hamilton-Jacobi equation using proper action. They solve that equation into first order differential, and that is sufficient for our shadow thing, right? So after this first order, we introduce impact parameter eta and zeta. Eta and zeta is very important because they reduce the number of variables. We are interested in spherical orbits because photon sphere is important for shadow. So we are interested in spherical orbits, and that for mathematically you have r dot, this r equation, r dot and r double dot is 0, and using this, if you solve these two equations, then we get two impact matter, the critical values of the two impact parameters. So this is the critical impact parameter for the spherical photon orbit. Now, if you want to resolve this, and mathematically it is equal to what? The effective potential, the extremum, local extrema or maxima at the effective potential, right? So that we have shown in this, and it is repulsive at the small distance. You can see very easily, it is repulsive at the small distance, and at large distance it is finite, right? So when we solve eta is equal to C equation, the two, then you get the spherical photon orbit. So we have two photon orbit, the counter rotating orbit and co-rotating orbit, and they lie in this region, and this solution is exactly for the Kerr black hole. However, because of the complex solution for the EGB, we are unable to solve, and we have solved numerically and plotted them in this. So this is the photon region for the 4D EGB, and the black is the shaded black is the disk, which is like black hole, and this is the photon sphere, region for the rotating Kerr black hole. It is slightly smaller compared to the Kerr black hole, and this is very important. This is the inner, and this is the outer. Obviously, the outer is bigger because of the Okay. So now we want to study the shadow. So we have to have use the celestial coordinate, because this we are projecting in the observer plane, in the image plane, and so we use the celestial coordinate xy. Now this first order differential is already shown you, that can be used, and we can exactly find xy like this. Right now, this is having same expression as the Kerr black hole. However, when you put these values, it becomes very complicated. Now, this is for the non-rotating case. I have shown in the for the non-rotating case. This is shown here, and for the non-rotating case, it is perfect circle, as we can see in this figure. Whereas if you take alpha is equal to 0, it will be curve, and it becomes distorted on the left when the angular momentum is very high, right? When we plot for the 4D EGB black hole, we can see that the black corresponds to the Kerr case, and you have smaller and then more distorted black hole shadow. So that is the crust of this. We have plotted for various parameters, and this 4D EGB black hole shadow theoretically casts more distorted and smaller shadow side, right? Now I want to apply this black hole shadow. We need to use this black hole shadow to estimate the parameter associated with black hole. The original paper was theoretically by Miyoko method, and there are many other methods. I'm saying about the shadow, right? So what they did, I'm not using this shadow. They have say a reference circle for the shadow, right? So they have shadow coincide with the reference circle. Now this is the problem with this method. The problem with this method is that you have to use particular particular symmetry to make a parameter estimation. They define two observable RS and delta. RS define the radius of the shadow, and the delta is the distortion. So as I said in the previous case, the 4D EGB, the radius decreases, so RS will decrease. Right. But we have proposed this in the paper given here down, FJ paper. Two more observable, which is area. Distorted is already there. Area is the area of the shadow, which can be calculated numerically. Numerically, right? So we define these two observable, and then distorted can be 1 for the Schwarzschild case, and it can be maximum √3/2 for the Kerr case, right? And then what you do, we plot them as a contour plot. We make a contour plot of A and D in alpha A plane, the plane of the black hole parameter. So we can see that area, black line is the area observable, D is the obliqueness. So in case of 4D EGB, you can see that the radius decreases as well as, and this distortion is very sharp. That's why I said it is more distorted and more smaller shadow size. So now I have made a plot. It is a contour. It is a contour plot. It is a contour plot of observable A and D. Red line is the area, and D is the distortion. D is the obliqueness, right? The point of intersection of A-D curves gives the unique value of the black hole parameter A and alpha. By using our method in general, we can maximally we can estimate two parameters associated with black hole. Parameter A alpha. You can estimate any two parameter, but we have shown A alpha, and this is the estimated values. So we can say that for a given A and D, the parameter associated with black hole is, for example, in this case, A is 0.346 and alpha is small value 34. So that is the parameter estimation. So this is important. This is very important. Now we can do for any black hole. I am not having time for that. Now, as I said, Singe was the original person to propose the black hole shadow, and then they gave the definition of angular radius, which we'll be using very frequently in this paper later. And Sagittarius A star angular diameter is for 53 macro arc second, and M87 is 20 macro arc. This is This two is important, and they are prior to the Event Horizon Telescope result. Right now, we know that the Event Horizon Telescope has released the picture of the M87 in 2019, and it happened. The observation was done in 2017. After 2 years of intense data analysis, they published the result in the form of 6 FJ latest papers. And basically, it is a radio telescope, Earth-size global array of radio telescope, and it is Earth-size telescope. Right. So Sagittarius observation was also done, but no data was released. Right. So the shadow of M87 is consistent with the Kerr black hole of general relativity, and it is an asymmetric ring with a bright emission ring. And the asymmetric ring is because of the strong gravitational lensing and the relativistic beaming. And disappearance is in the central region is the observation signature of the black hole. The mass estimated is 6.5, which is slightly higher than the previous estimates by other technique. And the gravitational this crescent diameter, angular diameter is 42 plus minus 3 microarc second. Oblate is
5 millions are left.
pardon?
5 millions are left.
Yeah. Oblateness is less than 4/3, and reported deviation is 10%. Right. So there was information about the orientation of the black hole, but no value was given. The mass value was higher, as I said. There were other objects, but they were found not to be compatible, like naked singularity and wormhole. But the boson star and Gravities star were not ruled out, and we want to constrain now 4D EGB with the event horizon. So there are two observable. We consider the circularity deviation. It is deviation from the circularity, which is 10% as pointed by the event horizon telescope. Right. So it measures exactly deviation from the perfect circle. So let's see what happens in the 4D EGB glass. The left hand side is 90 degree, and this is the right side is 17 degree, which was used by the Event Horizon Telescope. In the case of 17 degree, entire parameter space satisfies the circularity deviation. So it is very good because 4D EGB black hole is totally consistent in terms of this circularity deviation. But in case of 90, it is what this black line is at the 39 microarc second. 39 microarc second. We are taking 1 sigma bound on the Event Horizon Telescope. 42 they said, so 1 sigma 39, and this is the black line. So inside this line, it is satisfied. Here it is not satisfied. White region is totally ruled out. Right now, another is very important is angular diameter. Both observables should be satisfied. So angular diameter is defined by this, right? And they have given. We have plotted that for the 4D EGB black hole. Now this is the black line which at 39 microarc second. So we can see that in this case there are a lot of constraints, and a finite space. Of course, still there is a finite space satisfied by the 4D EGB for both 90 degree and 17 degree. So both should be satisfied, angular diameter as well as this. So we can say that the 4-dimension EGB black hole in the finite parameter space is consistent with the black hole with the Event Horizon Telescope. So lastly, conclusion: the rotating black hole shadow allows us to study the effect of higher curvature on the shadow of the black hole. Right, the radius of horizon significantly decreases. We have shown with the increasing Gauss-Bonnet parameter alpha. And the ergosphere is also affected. Therefore, shadow is also affected. The EGB black hole casts smaller and more distorted shadow, as I said before. We modeled the M87 star black hole with the EGB black hole and showed that it is consistent with the Event Horizon Telescope. So this I have already said. I will leave 2 minutes for question. Our results constrained 4D EGB very in the small way with finite parameter space. It is satisfied. So it is not ruled out. Even if there is a deviation, the deviation is at a micro arc second, which is not possible to be done by the event horizon telescope. Cannot be resolved by the event horizon telescope. So thank you so much, Njong, and I open to the question.
Thank you, Susan. Any question that we have about, let's say quickly, quick question. Okay, so if you do not have later perhaps we have about 15 to 20 minutes totally, then perhaps Susan, we will leave the question to the end of all the talks. Okay, so thank you very much. So perhaps let's turn to the next. I think perhaps people maybe want to ask you later. Thank you.
Okay.
Very nice talk. Yeah.
Thank you so much.
So
I will stop sharing.
Yeah. Okay. Let's turn to Professor Ballori. Yeah, his talk. Yeah. Okay. So, can you share the screen?
Okay.
George? Yeah.
Okay. So thank you. Good morning or good afternoon, depends on the location. This is a work done in collaboration with my student, my PhD student Byron Droguet, who is here in the audience and who is near to finish his PhD degree. And I'm going to talk about a very specific computation regarding the quantization of the non-projectable 2+1 Horava theory. So every one of us knows that Horava theory has been proposed as a quantum theory of gravity, but I think several important problems of the former problem of the theory remains to be solved. Perhaps the most important of them is to prove the renormalization of the non-projectable case, because the projectable case has been already proved to be normalizable. So, but the essential difference between these two cases is given by the fact that the non-projectable case has a second-class constraint. And I'm going to talk all the time about this fact, this important fact about the presence of the second-class constraint, and the research we do here is motivated by the fact to look at a consistent scheme of quantization with these constraints. So as I say, the projectable case has been proved to be renormalizable by this group here. The projectable case, since it has only a first-class constraint, it is a strict gauge theory, and you might use the standard technique of quantizing a gauge theory by using the Faddeev-Popov method and taking in advance the emerging of the BR-SG symmetry. What is not so standard in that case was the use of a non-local gauge, given by this expression. In particular, what is non-local is the Lagrangian, because the term of gauge fixing in the Lagrangian use this non-local operator. So, what is the idea? The idea is that with this gauge fixing, you obtain at the end a regular form of the propagators for all the modes of the original theory. And regular means this, that the propagator take a hyperbolic form in Euclidean space. This is very important to prove, I think this is the central step to prove the renormalization, since the authors were able to show that subdivergences in diagrams disappears once all the variables get regular form from the propagators. Some other analysis in the 2+1 projectable theory, and also in the 3+1 is, I can mention some studies about the renormalization flow given by the same group. In particular, they show that the projectable case is asymptotically free, and there are also some other analysis in the renormalization flow given by these groups here. Of course, there are other analyses very important on the quantization of both the projectable and non-projectable. Or actually, I mentioned just some examples. Well, but the projectable case is not so phenomenologically interesting or physically interesting as the non-projectable case, because it is not so close to general relativity, because you lack the Hamiltonian constraint as a local constraint, and you have only the momentum constraint, which is the generator of the spatial diffeomorphisms. But as you know, the Hamiltonian constraint at the end is the analogous of one of the components of the Einstein equation. So it is very difficult, I think, in this case, to get a physics near to general relativity, in contrast to the non-projectable case, in which case we have the hope to remain close to general relativity. So I think that from the physical point of view, it is interesting to analyze the non-projectable case. But the problem starts here with the fact that the non-projectable case has a contract constraint. So the idea is to look for a quantization for them. I think one approach, one important approach, is to consider the path integral and consider the measures associated to second-class constraint. For a long time ago, it has been known that the fact that you have to modify the measure when in the presence of second-class constraint, and this has to be done in Hamiltonian formalisms. I mean, it is not easy to, or the place where you have well-defined the measure associated to this constraint is in the Hamiltonian constraint. And for some cases, like in Horava theory, it is not easy to pass to the Lagrangian formalisms. So I think the best thing to do is to start with Hamiltonian formalisms. So this is the theory. In particular, in 2+1 Horava theory, I use the potential found by this group here. And as you know, this group here incorporated the terms given by this vector. The canonical formulation has this general structure. And the only first-class constraint is the momentum constraint, and you have two separate cases depending on where you are or not located at the critical point given by this case when the lambda is equal to the inverse of the spatial dimension. Let me show this quickly. This is well known. In the general case, or most known case, lambda is not critical. This is the Hamiltonian, and you get the second-class constraint is given by precisely the Hamiltonian constraint, which I can write in this general form. His partner is the vanishing of the momentum associated to the Leibniz function. At the end, you obtain, as it is well known, one scalar mode propagating in 2+1 dimension. But there is also the other possibility, and this is I'm not going to talk very much about this. This is just a comment that you might sit here in this point of the space of parameters, and in this case, you obtain two extra constraints, and the physical result is that you don't have any propagating mode in 2+1 dimension, exactly as 2+1 general relativity. So coming back to the generic case, when you have not located at this point, I start the quantization. As I mentioned, the idea is to consider the second-class constraint and consider the measure. This is the measure, the position of the constraint and the measure associated to them. And also, at the end, you have also first class constraint and a gauge symmetry associated to this constraint. So you have also in the Hamiltonian formalisms a measure defined from them. It's very similar to the Faddeev-Popov measure in the Lagrangian formalisms, but with the important difference that the measure for the first class constraint admits only canonical gates because it is defined in internal Poisson brackets. So it is limited in some sense. Continuing, let me comment that the second class measure simplifies by these particular forms. So at the end, we can incorporate in the Lagrangian by using fermionic gauge. This is very important because in principle, it is not trivial how to incorporate the measure in the Lagrangian and in the canonical Lagrangian, I mean. And at the end, you need a Lagrangian in order to extract consequences of the dynamic, for example, to obtain the propagator of the theories. We first focus the quantization using the reduced technique, which means integrate out as many of the variables you can using a simple gauge, like for example, the transverse gauge. This is very easy to work. And at the end, we reach with, or we end with these variables. These three last variables are associated to the measure of the second class constraint. And at the end, the rest of variables, like this one associated, this first one associated to the gauge symmetry, and these two momentum can be integrated without difficulty in the path integral. So you are close to the physical degrees of freedom, but there are still some unphysical degrees of freedom because we are interested in the sector associated to the second class constraint. The conclusion from this is that, or the main important result we obtain for this is that we can compute the propagator associated to these variables. And the result is that most of them takes a regular form, in particular, the last function take a regular form, but in any case, the new variables we have introduced in the process of incorporating the second class constraint to the path integral occurs non-regular propagators, and you might see this because they do not depend on the frequency. It is curious for me that they get at the end exactly the same form. This is the Lagrange multiplier associated to the Hamiltonian constraint, and these are the gauge associated to the measure of the second class constraint. So it is interesting that they take exactly the same form. So we might ask if maybe some cancellation can occur at the time of computing the Feynman diagrams. But in any case, we have not studied this deeply, so we are just studying some specific cases. The second part is to know to use this basic scheme of defining the path integral and not to take the reduced phase space, but on the contrary, to use a more advanced scenario in which you might extend the phase space and also to consider the second class constraint. So the point is that in the previous analysis, we use the transverse gauge as an example, which is a canonical gauge, and you can use the Faddeev measure for the first class constraint. But at the end, we know from experience with the projectable case that probably the best kind of gauge physics are this kind of gauge, which requires the use of this Lagrange multiplier. So it is a non-canonical gauge. So we might ask, how can we incorporate this gauge fixing in the Hamiltonian formalism since it is a non-canonical gauge? The answer comes from the BFB Batalin, Frankel, and Birkhoff quantization, which was precisely designed to incorporate non-canonical gauge physics in the Hamiltonian formalism. In principle, it was defined to relativistic theory introducing relativistic gauge, but at the end, we can check that it can be extended or used without problems to the case of Horava theory and non-relativistic gate condition as this one, which is clearly non-relativistic gate condition. So, in summarizing the BFB formalism, the main idea is that you don't have to impose explicitly the first class constraint, so the fadest measure associated to them disappear. They are imposed in the dynamic, of course, because they are constrained. You have to eliminate this degree of freedom or some degrees of freedom and the gate symmetry, but they are incorporated in a very indirect or very clever way by incorporating it to the BRST chart, the BRST generator, and the BRST generator, of course, modifies the Hamiltonian because you have to define a gate fixed Hamiltonian. So in some sense, this is similar to the standard BRST approach of the Lagrange, but in the Hamiltonian formalism, and the object that plays the role of the charge is this one. The charge is defined as an expansion of this gauge. Let me explain a little bit. The idea is that for these G functions plays the role of the first class constraint, but extended to some new variables called PA, which play the role of canonical momentum to the Lagrange multiplier of the original first class constraint. So once you have defined this extension,
5 minutes left.
okay, let me go first fast. You define this extension. The idea is to incorporate this extension to the Horava theory. A part of the new canonical momentum, you have to introduce new gauge, BFB gauge, for each of the first class constraints, which are denoted by this A and P. You define the phase space. The second class constraint is the same. You have to incorporate the measure, but you have the advantage that you don't need to use the FADF measure associated to the first class constraint. At the end, we can obtain, or we obtain the charge and the gauge fixed Hamiltonian with any fermionic function playing the role of gauge fixed condition. You have to prove that the formalism is consistent by these two non-trivial conditions. We get that the BRST symmetry emerged, and this is the transformation in the Hamiltonian formalism for the symmetry. We incorporate the last step is to incorporate how to incorporate the gauge fixing. So this is the famous form of the relativistic gauge the BFB author introduced. But at the end, since Chi can have any form, you may modify it in order to include the non-local operator. The only price to pay is that in order to balance and to write all the gauge fixing as a non-local gauge fixing, as was the idea in the projectable case, you need to perform a canonical transformation, because now the Lagrange multiplier is a canonical variable in the BFB formalism, and this is its canonical momentum. So no problem, you perform a canonical transformation, and all the original gauge fixed condition can be written in a non-local form. And after doing this, let me show to finish a specific computation with the perturbative action. The only thing that is non-defining is the non-local operator. So the idea is that you can extract dynamics from this action. We showed, so to finish, we showed that BFB formalism can be incorporated to the non-projectable theory. So we think that this is a small advance in the program of proving or defining a well quantization scheme for the non-projectable theory and the second class constraint. And perhaps we are advancing in the proof of the renormalization. At the end, the bad news is that these variables get also non-regular propagators because they don't modify the fact that they don't get time derivatives. So some station is to advance by using the explicit expression of this local operator, but adapted to the BFP formalism. We are studying this with another student, Claudio Borges. Perhaps to perform integration in the momentum sector to obtain Lagrange. And at the end, since these variables are not regular, what about if some cancellation can occur when, at the time of computed Feynman diagram? So this is the end. Thank you very much.
Thank you very much, Judge. I think perhaps the time exactly 10:15. Perhaps I will leave the question at the end of the talk. So thank you very much, Judge. It's nice talk.
Perfect.
Yeah. Let's turn to our next speaker, Dr. Jarvan. Can you share your screen?
I can share my screen.
Yeah, please go ahead.
Can you see my screen?
Yes, we can see clearly. Go ahead.
Okay, thank you. Let's start my talk. First of all, I would like to thank all the organizers of this conference, MG16, to arrange such a nice conference. Special thanks to Professor Anzeng Wang for giving me opportunity to deliver a talk in this conference. Thank you very much. The title of my presentation is Cosmological Implications of Einstein Ether Theory of Gravity. Basically, I will discuss cosmic acceleration with the help of Einstein ether theory of gravity and expose my ideas. This work is co-authored by Professor Dr. Kazuhara Bamba from Japan. Here's the layout of my presentation. I will discuss some cosmic expansion initially, and then I will discuss reconstruction scenario between Einstein ether theory of gravity and dark energy models, and then I will conclude my results. So here's the current scenario of the universe. The current status of our universe has been obtained under the various observation type 1 supernovae. And in its developing process, the universe passes transiently through different phases, eras, namely Big Bang, inflation, radiation dominated phase, matter dominated, then tends to dark energy dominated era, that is present era, and this is supported by dark energy. And our universe is accelerating at present time, and this accelerating is due to the dark energy, which has repulsive force, which has two remarkable features. First one is the repulsive force, and second one is it does not cluster at all at large scales. So in order to discuss cosmic acceleration, before I will discuss major constituents of the universe. Basically, two major constituents exist in the universe: matter, which is also called dark matter, and dark energy. So dark matter can be characterized in two forms, like baryonic dark matter and non-baryonic dark matter. And baryonic dark matter is only 4.9%, which consists of everything which we can see, so like stars, galaxies, planets, and in which we can see. And the other one, other 26.8% is invisible matter, which also exists in the universe, but it cannot be detected directly, and it can be directed through the effects of dark matter on visible dark matter. So this idea is proposed by Zwicky in 1930 in order to discuss the dark matter, which is invisible, exists in our stars, galaxies, etc. And the major constituent of our universe is the dark energy, which is discussed today, which is possible way of to explain the cosmic acceleration. Dark energy consists of 68.3% in our universe according to Planck data. So this is a constituents of the universe through a picture which consists of so many constituents, but major constituent is dark matter and dark energy. So in order to explain cosmic acceleration, in the presence of dark energy, there are different views, different proposal in order to discuss this phenomena. First one is the modified theories of gravity, and second one is the dark energy models. If we modified Einstein field equations, its geometric part, like Ricci scalar with the different other forms of function of different modified theories of gravity, then we can replace Einstein theory of gravity with f of r, f of t, f of g, frt, frg, as Einstein ether theory, etc. There are different other theories exist which we cannot incorporate in this talk. Majorly, I will discuss here Einstein ether theory and its combination with different dark energy models. Basically, the first one is the modification of the geometric part of the Einstein field equations, which is proposed by modified theories of gravity. And the second one is the dark energy models, which can be modified the matter part of the Einstein field equations. There are different modified dark energy models exist in the universe and proposed by different researchers and scientists in order to explain cosmic acceleration, like quintessence, chaos sense, holographic dark energy, and its modification dark energy models. Basically, holographic dark energy model I will discuss here. Holographic dark energy is based on holographic principle, which is proposed by G.T. Hooft in 1993 on the basis of Bekenstein-Hawking relation on entropy area relation. So, with the help of G.T. Hooft idea, different researchers work on it and proposed a dark energy model called holographic dark energy model, which I will discuss later on. And its modification also exists in the literature recently by using non-extensive entropies of the universe, like Tsali entropy, Rayleigh entropy, and Sharma metal. And nowadays, Barrow entropy is also exists. And based on procedure of holographic dark energy models, they proposed different dark energy models based on Tsali entropy, Sharma metal, etc. So that's the picture to elaborate the cosmic acceleration mathematically. If we take second Friedman equations, this equation of state parameter. For example, we can explain different eras of the dark matter, which can also be concluded as decelerated phase, and cosmic acceleration era, which also can be known as accelerated phase of the universe. For example, if we have omega lie between 0 and 1, we have radiation phase, and omega 0 represent cold dark matter, mean pressureless matter, and in the second phase, mean accelerated phase, we have omega less than -1 and greater than -1/3. We have quintessence era, in which cosmic acceleration is lower than other phases, like vacuum energy, mean cosmological constant, where omega is equal to -1. And omega is equal to omega less than -1 represents the phantom acceleration or super acceleration of the universe. So here's the picture to elaborate the different possible models of the universe, mean radiation, dust, uh, by using equation of continuity and first Friedman equation. First Friedman equation will give us a Hubble parameter. Firstly, we solve equation of continuity in terms of scale factor by setting omega is constant, and which gives a Hubble parameter by using first Friedman equation, and then we can solve Hubble parameter. We can get a scale factor in terms of in terms of equation of state parameter. So if we change equation of state parameter, like previous slide, we can get the different solutions of the scale factor and energy density. If we have omega is equal to 1/3, we have a scale factor in terms of cosmic time, square root mean, and rho density depend upon the density is inversely proportional to the scale factor. And in the second case, if we omega is equal to 0, we have dust case, and in this case, density become this one. So in other cases, we can also obtain the solution of energy density and scale factor by setting their values. So in order to explain cosmic acceleration in another way, or in order to describe or distinguish different dark energy models which are present in the literature, we can use the tool omega prime plane. Omega prime represents the evolution of the equation of state parameter with respect to the natural log of a. This is a basically standard parameter to describe the different phases of the universe. So this tool is proposed by the Caldwell in 2004 in order to describe and characterize the regions of the universe by freezing and thawing region. In thawing region, we have less acceleration as compared to the freezing region. If we omega prime greater than 0, omega less than 0, we have thawing region. We will discuss these two thawing and freezing region for our models in the later slides. And for omega prime is equal to 0, omega is equal to -1, we have lambda CDM model. So in order to discuss the instability of our models or constructed models, we can use scared speed of sound. Scared speed of sound, as equation of state parameter discuss the evolution of the universe, the scared speed of sound indicates the stability, instability behavior of this evolution. Its working methodology depends on energy density perturbation from the theory of linear perturbation. First, the conservation law of energy momentum tensor gives perturbation energy density involving scared speed of sound. In some more simplification for real solution, we have to take Vs square greater than 0 or Vs square less than 0. It means Vs square is less than 0 represents the unstable behavior of the universe of the model, or if Vs square greater than 0, we have stable model of the which can exhibit the stability of the models. So Einstein theory basically utilized in order to discuss different possible solutions of the models. For example, in order to discuss accelerating universe in Einstein theory, I have been studied Barrow in 2012, and different cosmological evolution of cosmological models on based on Einstein theory with power potential also V et al. It was observed that in such models, the universe experiences a late time acceleration for pressureless mean dust matter. The action of Einstein theory is given here. Here, Lm represents the matter density, matter Lagrangian density, and Le represents the Einstein theory Lagrangian density, which depend upon the different functions and constant parameters, where k is the basically basic argument of the Einstein theory, and k for the FRW metric becomes in terms of Hubble parameter, which is basically a variable, epsilon, and m is constant, h is variable, so k is a variable here. So total dependence of Einstein theory is on function of k. We will develop function of k in the presence of different dark energy models and discuss their cosmic evolution. Anzeng Wang et al. Also discuss spherical solutions by using this theory. So motivation is here in order to discuss the corresponding procedure between dark energy models and different dark modified theory of gravity will be addressed here and discuss their cosmical evolution. Here we choose the flat FRW universe. However, in general, FRW metric is given here. Its basic entity is a scale factor, and k represents the curvature of the universe, mean geometry of the universe. If k is equal to 0, we have flat universe of flat geometry. If k is equal to -1, we have open universe of negatively curved, mean it expands forever. And if we have k is equal to +1, we have positive slope. It will goes to the end of the universe. So we consider here k is equal to 0 flat universe, mean asymptotically flat universe. So far, in general, Friedman equations for FRW metric can be obtained in equation 1 and 2. Here f prime represents the derivative with respect to k, and kappa is basically different. Kappa is represent the geometry of the universe. FRW metric, however, capital K is the basically basic entity of Einstein ether gravity. So in this case, right hand side represents the geometry of the geometry part of the universe, and the left hand side represents the left hand side represents the geometry part of the universe, and right hand side mean matter part of the energy momentum part of the universe. So these equation can also be described in different way in effective form, equation 3 and 4. We utilize power law scale factor in order to get our solutions or cosmic scale factors. Power law factor depend upon the cosmic time, and m
About the sir, you have 5 minutes left.
okay.
Yeah.
So if 8 is here, a naught is the scale factor present time, and t is the cosmic time, m is should be greater than 0 in order to evaluate the universe. So we will utilize different dark energy models, for example, Tosalis and Rene in next slides. Tosali model is given here, depend upon the which is obtained through Tosali entropy by adopting procedure of the holographic dark energy model, and it depends upon the IR cutoff. And for, in our model, we utilize IR cutoff as Hubble horizon, which is 1 over h. In terms of Hubble parameter, energy density become this one. And by using this energy density and Einstein ether energy density, we can get the differential equation, this one, for obtaining solution, this one, in terms of equation 10, where f of k is the solution of the Einstein ether function in terms of k. So we utilized this function in different quantities like energy density and pressure, and equation of state parameter. We get equation of state parameter in the cosmic time, and can be this can be analyzed through a graph given in figure 1, and we plot the graph of the equation of state parameter in terms of redshift parameter by using this transformation, and we can see that the plot shows the trajectories with respect to power law scale factor parameter like m, 2, 3, and 4. All the trajectories lies in the phantom era of the universe. So its evolution is given here, equation of state parameter, and its plot is given here, and thawing region. Sorry, here is the thawing region, and here is a freezing region. And for m is equal to 4, we have thawing region obtained, and for m is equal to 3 and 2 and 3, we have freezing region. So in this case, we have obtained both regions for different possible ways of m, which is scale factor parameter. So stability parameter given here after some calculation in the presence of dark energy model, Salis and Einstein ether, we can get equation 15. Its plot is given here, and we obtain unfortunately unstable behavior, and we can get the stable behavior for other choices of constant parameters, which can we try in future works. So here's the Rene holographic dark energy. Rene holographic dark energy is given here based on the Rene entropy, which is non-extensive entropy, and by adopting procedure of usual holographic dark energy, Muradpur et al. Obtained the Rene holographic dark energy in terms of Hubble cutoff. In terms of IR cutoff, we can utilize different IR cutoff, but here we can choose Hubble horizon. So dark energy in terms of Hubble parameter is given in 17. So by adopting previous procedure, we can get the function of Einstein ether theory in this case, and its energy density and pressure are given here, and corresponding equation of state parameter is given here, and it depend upon the different constant parameters and basic entirety of Einstein theory of gravity k. So we plot it in terms of a redshift parameter. So it means Hubble equation of state parameter remains in the quintessence era of the universe for all 3 cases of m. Basically, this is also compatible with the recent observations sent by the Planck data. So its evolution plot is given here, and we can see that freezing region of the universe only in this case because omega prime less than 0 and omega e less than 0. So in this case we have only obtained freezing region, which is super acceleration region of the universe. So here is the scared speed of sound. Its plot is given here, and we can obtain stability only for m is equal to 2 in later epoch. And for other models, for other cases of m, we obtain scared of speed of sound less than 0, which exhibits the unstable behavior of the universe, unstable behavior of our model. So here's the concluding remarks. We have explored cosmological parameters by taking Sally's holographic dark energy and any holographic dark energy models in the frame of Einstein ether gravity. So in Sally's case, we have obtained only phantom era and freezing region, thawing region for only m is equal to 4.
Hello, Abanu, are you there? Or you finished? Can you hear us?
And
Okay.
there.
Go ahead. Okay. Thank you very much, Abanu, for your talk. I think the time is over. So perhaps I will leave the question to the end of this session. So next is our speaker, Dr. Lisa Campos. Lisa, can you hear me?
Yes, yes, I can hear you. Hey.
Yeah, please share your screen now. You
Yes.
can. Yeah.
Okay. Should I turn my video on? Or people do? I don't know.
We can hear you clearly.
What? Can you hear me?
Yes. Go ahead.
Okay. Okay. So, okay, no, I'm gonna turn my video. Is that okay? Okay.
Yeah.
Okay, so hi. All right, so first, yes, thank you for the organizers for putting this together, and thank you, Professor Wang, for organizing this session and giving me the opportunity to present my work. So my name is Lisa, and I'm a PhD student in Pavia in Italy. And I've been working actually with quantum field theory on curved spacetimes. And my goal here is to talk about how we can choose boundary conditions for the Klein-Gordon field on Lifshitz spacetimes. So the context is this. Wait, it's not going. Okay. So I will consider a free scalar massive quantum field theory on a 4-dimensional Lifshitz spacetime with critical exponent z equals 2. So I don't actually work with Horava-Lifshitz theory. I work with quantum field theory, but the methods do apply in this case. So like it's kind of like, well, the methods apply on Lifshitz spacetime, and maybe something can come out of this. Okay, so the idea is this is Lifshitz spacetime, 4-dimensional one. We have a singularity at r equals 0 and the Lifshitz boundary at infinity. And if you consider a massive field on it ruled by the Klein-Gordon equation, for certain values of the effective mass, mu, so actually for negative values of the effective mass, we can impose different boundary conditions from Dirichlet, so robbing boundary conditions at the boundary. And each robbing boundary condition, each boundary condition yields a different physics. So if you prepare your system in a certain state, it can evolve to different things. And we usually, well, sometimes we can interpret what these things mean, and then we choose the boundary condition depending on the scenario we're considering. But sometimes, such as this case, when we're dealing with more, well, with quantum field theory on curved spacetimes, then we can't actually choose just using physics. I mean, actually, the point here is I want to show how we can construct 2-point functions for all admissible boundary conditions. So among these robbing boundary conditions, some of them yield physically sensible evolutions, but it's still not unique in the end. Okay, so fix the 4-dimensional Lifshitz spacetime with critical exponent z equals 2. I'm going to show how we can construct a ground state and the KMS state, which is a thermal state for a massive scalar quantum field theory, which is, okay, this work I'm going to present is a joint work with Professor Claudio De Piaggi and then Messina, which is on archive. Okay, and to do that, first I'm going to briefly solve the Klein-Gordon equation, construct the radial Green function, rule out the poles of the radial Green function, and with this, we can construct the 2-point functions. So this is the outline. Okay. Well, also I planned like a 15-minute talk such that we would have like 5 minutes of question in the end. Let's see how it goes. So first, solve the Klein-Gordon equation. If we take the Klein-Gordon equation on the Lifshitz spacetime, 4-dimensional critical exponent 2, we can do a mode decomposition because it's a static spacetime and the sections of constant time and radius, well, are actually flat. So here y is just the harmonics, the eigenfunctions of the Laplacian operator on R2. Okay, we can do this mode decomposition and we are left with a radial equation, which is an equation for the radial function. And this radial equation we can actually cast as a confluent hypergeometric equation by applying a transformation on the independent variable and another transformation on the dependent variable. So we are left in the end, actually, the Klein-Gordon equation gives us a confluent hypergeometric equation with these parameters A and B here that depends on this auxiliary parameter nu, which depends on the effective mass. So depending on the effective mass, we can have different boundary conditions. And now instead of talking about mu, I'm going to talk about nu. Okay, that was very, okay, yes. And we can use the solutions of the confluent hypergeometric equation to write down the solutions of the Klein-Gordon equation, okay. Yes, I said stuff, okay, yes. So nu is what I'm going to talk about now instead of using the effective mass, but okay. So the solutions of the Klein-Gordon equation, they are written in terms of the confluent hypergeometric equations, and there are two linearly independent solutions, which are the Kummer U and Kummer M, or confluent hypergeometric U and confluent hypergeometric M, but they are not numerically satisfactory at both endpoints. So we actually choose different bases at different endpoints, and we check conditions for these solutions to be square integrable because there is a one-to-one correspondence between square integrability and boundary conditions and self-adjoint extensions that we can impose, that we can obtain, and those are in correspondence with positive energy and physically sensible dynamics. Okay, so what we have is actually that the R = 0 singularity is a limit point, so we don't actually need to choose boundary conditions there, but at R = infinity, for those values of effective mass, so for n going from 0 to 2, which is tantamount to this thing I said at the beginning, the interval obtained by Keeler, okay, we can impose other boundary conditions, okay? So if we do that, if we consider this regime of these effective masses where we can consider different boundary conditions, we choose the only solution we have at the R = 0, and we put a Robin boundary condition at R = infinity, and we can construct the radial Green function by standard methods. So we define the normalization given by the Vronsky, and it's simply a simple product like this with heavy sides, and this is the radial Green function by standard methods. Now, what we have to do is actually to rule out the poles of the radial Green function, right? Because this function, n of omega, the normalization, depends on the frequency, and it can be 0 for some certain values of gamma of boundary condition. So here gamma parameterizes the boundary condition. Okay, so these functions are given by this, and we can define an auxiliary function, this xi, and the normalization is 0 when this xi function equals the tangent of gamma, which is always true. I mean, we always can find a gamma such that this equation holds if xi of omega is real valued. So that's the condition that we check. And if we do that, so the first thing that we obtain is that this function can only be real valued for purely imaginary frequencies. And then if we study this function as a function of purely imaginary frequencies, we get a very different behavior depending on the value of the effective mass. So if we do that for the first case from ni going from 0 to 1, we obtain something like this. So xi is real valued from a certain finite minus negative number until 0. And for all of these values, we can find a gamma such that xi of omega equals tangent gamma. But if we want to impose the same boundary condition on all modes, then we cannot consider this lower part, because if we take the limit for all modes of this lower bound, then that lower bound goes to minus infinity. But in any case, we still have this upper part, and this upper part, I mean, there are no omega such that xi of omega is positive, right? So we still have those values, and we can consider gamma from 0 to pi over 2, which gives us, well, many Robin boundary conditions for which there are no poles. And the situation changes drastically when we consider the effective mass. Oh, here's wrong. It should be from 1 to 2. So if we consider from 1 to 2, then the normalization has, this function has a pole. And if we want to impose the same boundary condition for all modes, so now in this case, xi goes from minus infinity to 0 and from a positive finite number to infinity. But if we take the limit for all modes, this positive lower bound here actually goes to 0, and we are left with only Dirichlet. And yet, if we can impose mode-dependent boundary conditions, then we still have a region of boundary conditions that we can impose for each mode. So in the end, this is what we obtain. So for the pole analysis for Dirichlet, we can always do it. There are never poles for any masses. Nice. For Neumann and the Robin boundary conditions, well, they can all, anything that's not Dirichlet is sometimes called Neumann as well. It's arbitrary, but okay, I call them Robin. So yes, so there is an interval from 0 to a limiting value that we can impose for which there are no poles, right? So, but this interval, this limiting value is different for different masses. And yet, if nu goes from 0 to 1, we can impose many boundary conditions. Okay, I'm going to summarize this more precisely soon. Now, if we do that, we can choose the boundary conditions for which we have physically sensible dynamics and for which the green function will have no poles. So we do that. Oh, and this is compatible with this previous work, okay, where they showed that instabilities emerged, and the other in the second range of effective masses, where we have that pole and this, and the only allowed boundary conditions are mode-dependent ones. Yes, okay. Now, if we want to construct let me see, what time is it? Okay, 10:49. Okay, if we want to construct the two-point functions, we can make this ansatz, which is basically a sum of modes. And this function, g gamma of omega, is constructed from the radio equation from the radio green function that we just constructed. The function t is straightforward because, for example, if we're talking about the ground state, we want this to have support only on positive frequencies, and it's a static space-time, so we know how it looks like. And the harmonics, we also know how they look like. So, but this ansatz cannot be anything because the anti-symmetric part of the two-point function is actually the causal propagator, which is a green function of the Klein-Gordon equation such that it satisfies these two initial conditions. So these two initial conditions on the anti-symmetric part, on the causal propagator, is equivalent to the canonical commutation relations in a covariant form. So something like this. So if we impose the canonical commutation relations on the anti-symmetric part, we actually restrict the form. Well, I mean, we restrict the form of the function g gamma of omega, and it must satisfy this identity. Okay. On the other hand, if we take the radial green function that we had before, and okay, yes, okay, so we take that and we consider this identity. Now let's go to the if we consider this radial green function, we can actually do some spectral analysis here, because from spectral, there is the spectral resolution of the radial green function on the complex plane satisfies this. So this equation. So this is an identity. And since we're choosing boundary conditions for which we have no poles, the sum over the poles disappear, and we are left with a contour integral being equal to a certain delta. And if we compare this identity from spectral theory with that identity from imposing the canonical commutation relations, we have this equation here. And if we can do the contour integral, which we can in this case, and we can actually find out g of gamma of omega through this identity, then it's done, right? So in this case, we can do it, and it looks like this. So this is actually real valued. Okay, it's nice. So we have the function g, and the function t, as I said, we actually know what it is. So it looks like this. So for the ground state is a simple, well, Fourier parameter, let's say. And for the thermal state, there is like an exact balance there, but precise. We choose it in such a way that there is a precise balance between the positive frequencies and the negative frequencies, such that it will satisfy the KMS condition. So it looks like that. So with those Boltzmann factors. Okay.
Lisa, you have 5 minutes left.
Yeah, I'm almost done. Thank you. Okay.
Okay.
Now, in the end, the 2-point function is actually, if you construct it like this on a static spacetime, such as this one, it is guaranteed to be of local Hadamard form. It is guaranteed to yield physically sensible dynamics because we considered self-adjoint extensions and square interval solutions, and it satisfies the canonical commutation relations. So this is a physically sensible boundary condition dependent 2-point functions. Okay. And in the end, this is the goal. This is the conclusion, actually, that there is a plethora of Robin boundary conditions that yield physically sensible inequivalent dynamics for the Klein-Gordon field on Lifshitz spacetimes. So that table that I had before actually can be written like this. In terms of the effective mass I give at the beginning, it looks like this. So there is a certain value, certain interval of effective masses that we can impose many mode independent boundary conditions. But in the second interval, we can still impose mode dependent boundary conditions. And in addition, we actually considered Lifshitz topological black holes obtained by Mann. And we did a very similar analysis there. Everything works analogously, though the Ritchie scalar is position dependent. So we get like more complicated conditions, but it works, and that's it. So I guess we can have some questions now. Okay, thank you.
Yeah, thank you very much, Lisa. Any question to Lisa?
Yeah, I actually, if I may.
Yes.
Oh yeah, go ahead, please.
So I have a question. Can you construct a green function for Horava-Lifshitz theory in FLW background or something like that?
In what background?
Friedman, Lemaitre, Robertson background.
Robertson.
Is there any specific reference for that?
Well, I mean, you can do it, but if you can use exactly this method, I'm not sure, because that's not static, right?
It's certainly not.
Yes. So, but I mean, in some cases you can still generalize it, but I don't know. Yeah, this definitely applies on static spacetimes. It does apply on rotating, like on the rotating BTZ, it worked, but on Friedman, Lemaitre, Robertson work, I think it would be a different analysis. Like, well, I mean, actually, you can do that, but like I'm not sure what you mean. Like you can construct the 2-point functions, but you cannot invoke the same results I did. Like, let me go back here. Like, you cannot use this result, for example, like to guarantee that it is of local Hadamard form, and you cannot take exactly the same ansatz that I did, but you can construct it like using invoking different results. That doesn't make sense.
Okay, I see. Because I'm asking because I've been looking for some time to find some, let me say, general result for that, but I didn't found, so hence.
Oh, okay. Well, there is a paper from Claudio and Claudio Da Piaggi and Nicola Pinamonti. They did like quantum theory. I think I have it right here actually on my table. They did on cosmological spacetimes. So they have. I guess I can give you that reference. It's very interesting. They constructed it like it's a different thing, but they do construct it and it's very interesting on cosmological spacetimes, and it's interesting. I don't know, maybe I can send it to you.
Yeah, so if you could send me on this private chat here.
Okay, so wait, who is asking me? Because I can't actually see Zoom precisely.
It's Jan, J-I-N.
Oh, okay. Okay, yes, okay, I'll send it soon.
Thanks.
Okay, thank you very much, Lisa. I think the time is the exactly time. We should actually take a 5 minutes rest, then come back for our second section. Thanks to all our speakers so far. So let's take a pause, 5 minutes, please.
All right, thank you.
Okay, I think now let's start our second part. Our first speaker of second part is Professor Panatopoulos. Are you there?
Yes, I'm here.
Okay, so can you share the screen?
Yes, let me try.
Uh-huh.
Hopefully it will not take long.
Gregory, are you using PDF or
PDF,
oh yeah,
PDF,
now we
yes.
can see. Okay, good, very good. Yeah.
Okay, so can I start?
Yeah, please, go ahead.
Okay, thank you. Good morning, everyone. My name is Grigoris Panatopoulos, and I wish to thank Professor Wang for the invitation and congratulate the organizers for their excellent job. So today I shall be talking about strange quark stars in Horava gravity. Yes, it's better to use this option here. Oh. Yes, like to, yeah, sorry about that. My computer is getting slow sometimes. So first I will try to motivate the work. Then I will briefly describe for you how to describe relativistic stars in general relativity. After that, I will discuss the implications of Horava gravity on strange quark stars. And finally, then I'll present and discuss the numerical results. And finally, I will conclude. So I think everyone agrees that Einstein's general relativity is both beautiful and very successful theory. Over the years, it has passed several tests and many different predictions have been confirmed. For instance, one can mention solar system tests, the existence of supermassive black holes at the center of galaxies, and also indirect and direct detection of gravitational waves emitted from binary systems. So despite the success of GR, there are good reasons to believe that it should be extended at some point. for several different reasons. For example, one can mention the current cosmic acceleration. So there are several data coming from cosmology and astrophysics showing that the universe is dominated by dark energy, the component that accelerates the universe. So if one wants to accelerate the universe, one way to do it is to go back to field equations and modify the geometric part. So one can imagine an alternative, a modified theory of gravity, in the framework of which one obtains additional correction terms in the field equations. And these additional terms that are of geometric origin can play the role of dark energy that accelerates the universe. Another argument is that GR, unfortunately, is a non-renormalizable theory. And it was known from the 70s that if you consider higher order operators, then you can get renormalizable theories, but at the same time, unfortunately, you get ghosts as well. So one solution would be to abandon the idea of Lorentz symmetry. One can imagine that Lorentz symmetry is not a fundamental symmetry, and since it is not tightly constrained experimentally, we can entertain the possibility of standing Lorentz violating theories. So since these two original works, there is some activity on the field. So there is also this Einstein ether gravity, another Lorentz violating theory formulated by Jacobson almost at the same time with Horava theory. So here is what happens in the framework of these theories. You obtain modified dispersion relations suppressed by some high mass scale. So at low energies, this term can be ignored. You obtain the standard dispersion relation. But at high energies, the Green's function exhibit a better ultraviolet behavior, and this improves. It's good for renormalizability. So now, how to test extensions, new gravitational theories beyond GR? One way to do it is to consider astronomical objects, in particular compact stars. They are good. There are two advantages of this. First, they are exist in the universe. They come for free. And the other thing is that since they are very dense, one expects that gravitational effects will be very important there. And so one can try to study and constrain non-conventional gravitational theories. So on the one hand, there are neutron stars and white dwarfs that are well established. And on the other hand, there is another class of compact objects that are made of quarks, of deconfined quarks. And although they are less standard, they are quite interesting. They are very well motivated, and they can offer certain advantages. For example, one advantage is that the mass, the equation of state, the equation of state is known analytically. Whereas in order to study neutron stars, one has to use tabulated equation of states and do the whole work numerically. So the other thing is that if you look at the mass radius profile for neutron stars here in red and for quark stars here in blue, you see that quark stars are somewhat lower. And in fact, there are some real objects that have been observed that exhibit peculiar features, for example, low radii, that cannot be explained by hadronic equations of state. And this is one argument in favor of strange quark stars. So these real observed objects are considered to be good quark star candidates. And the other advantage is that since a configuration that consists of quarks is more stable compared to a configuration that consists of nucleons, it can explain the puzzling superluminous supernova that are 2 orders of magnitude brighter than usual supernova and take place 1,000 times less frequently. So within GR, in order to study relativistic compact stars. First, in the exterior problem, we find vacuum solutions where matter is not present. So in this case, one obtains the well-known Schwarzschild solution. And then inside the star, where matter is present, one obtains the standard Tolman-Oppenheimer-Volkov equations. Yes, so here. So we integrate the equations starting from the origin, assuming some central pressure. And then at the surface of the star, we match the exterior to the interior solution. And these two conditions allow us to compute first the radius of the star and then the mass of the star. Now, if you imagine an alternative theory of gravity, the structure equations describing hydrostatic equilibrium are modified. This is very sketchy in concrete theories. These new modified generalized structure equations can be very messy. And in particular here, I want to focus on this Horava theory or Einstein ether theory. At least at Horava theory, at low energies, it is equivalent to Einstein ether theory, and this has been shown by Jacobson. So if you write the action like this, so the space-time volume is separated like this. We write separately the the volume for the usual free space and time, which acts like a scalar field called the chronon. Then, via this scalar field, one can define a vector field and write down the Lagrangian in this general form with two coefficients C1, C2, C3, C4. And this is the Lorentz violating vector field. And so overall, this is a tensor vector theory. Now, if one is interested in non-rotating neutral, electrically neutral objects, this is the general metric at such for the gravitational field. And the structure, the continuity, the fluid equation remains the same. But the structure equations now, one obtain new additional terms that are proportional to this parameter nu, which is the only free parameter in the theory measuring the deviation from general relativity. And essentially this tells you, yeah, as you know, in general, in modified theories of gravity, one has the real neutron constant and some effective neutron constant that are not the same. And this parameter nu tells you what the difference is between the two. Now, the exterior solution in this theory is not Schwarzschild anymore. It's a more complicated solution, but it is known. So the metric potentials are certain functions of the radial coordinate r. Now, in order to compute the properties of the object, one needs to supplement the structure equations, assuming with the given equation of state. For quark matter, we use we adopt the MIT back model, and there are two cases. One is a linear equation of state. So the simplest one that has been extensively used in the literature is this one, when the mass of the S quark and the QCD coupling constant are zero. But more generically, depending on the values of B, the Planck constant, the mass of the S quark, and the QCD coupling constant, you obtain different values for K and rho naught, but still you have an analytic equation of state that is it's linear. And then if you take into account superconductivity effect, you obtain a slightly more complicated nonlinear equation of state, but still known analytically. Delta is the superconducting gap. So in order to find well-behaved, acceptable solutions capable of describing realistic astrophysical configurations, one has to check several things. Causality, for example, if the factor of compactness respects the Buchtel's bound, if the relativistic adiabatic index is larger than this certain value, the Newtonian limit, and finally, if energy conditions are fulfilled or not. So this is our main results. First, this is the mass radius profile. On the y-axis, we put the mass of the star in solar masses. On the x-axis, we put the radius of the star in kilometers. This plot corresponds to the linear equation of state. And we have considered for the parameter mu two values different than zero, while the zero value corresponds to gr. So here, in this case, we have considered three different linear equation of states for different values of k and ρs. And you see that within Horava-Lifshitz gravity, the profile is shifted in this direction. So the largest radius and the largest mass are reduced compared to the gr case. And this is the similar plot, mass to radius profile, in the nonlinear case for the same values of new parameter and for two different nonlinear models. So here we see the factor of compactness as a function of the mass of the star. So the numerical values of the parameters are the same as before. First for the linear equation of state and then for the nonlinear equation of state. And you can see that the factor of compactness takes the value up, does not exceed the 0.3 value. So they are compact, but they do not reach very close to this bound. So the rest of the conditions. So here we show the relativistic adiabatic index and as a function of the radial coordinate. So this goes from zero to the surface, from the center to the surface of the star. So these are for the same value of mu, 0.02, and for one linear model and one nonlinear model. And you can see that the gamma remains always larger than 4/3. The speeds of sound throughout the star take values between 0 and 1. The energy density is positive and the pressure is lower than energy. So it's straightforward to see that all energy conditions are fulfilled. And so this demonstrates that the solutions obtained here are all well-behaved solutions, satisfying all these reasonable considerations. So to conclude, there are good reasons to study alternative theories of gravity. One of them is Horava gravity, which is, I think, the main reason to introduce it is to improve renormalizability, UV behavior of Green's function. And then relativistic compact stars are natural cosmic laboratories, ideal cosmic laboratories to study and constrain non-conventional gravitational theories. Strange quark stars are interesting objects that they serve as an alternative to more standard neutron stars, as they can explain superluminous supernova, and at the same time they are good. Certain observed objects with peculiar properties are considered to be good quark star candidates. Here in this work, we have studied the impact of Horava gravity or Einstein ether theory, because, as I said, at least in the low energy limit of Horava gravity, the two are equivalent. We have studied the impact of both theories really on strange quark stars. Yes, in order to formulate the problem, we need to find the generalized structure equations plus the equation of state describing the microphysics of the matter content of the star. And we have found well-behaved solutions that are capable of describing realistic astronomical configurations. So that's all, and thank you for your attention.
Thank you very much, Gregorius. You finished actually on time. Actually, you finished, yeah. Any question, please? So I have actually two questions, Gregorius, about this very beautiful work. How, what's the parameter, the copying constant that you choose in your plot? You have several plots. You know, the theory has actually, for the Horava theory, there are three parameters. This is called, so how do you choose those parameters? The copy in the Horava theory or Einstein ether theory? You have a copy.
Yes, but if you see, yes, sorry. Yeah, if you see the precise expressions, you will see that they are not independent. Only one quantity is independent, and all the rest can be computed in terms of that. So, yes, here in the to study spherically symmetric, electrically neutral spherical objects, when you write down the structure equations, the only parameter that counts is this. So there is a single. It is a single parameter study.
Yeah, I think
Yes,
normally
but
it's
I'm almost sure that
C4.
all the rest can be computed, are given in terms of nu. So if you know nu, you know all the others.
Okay. So if I remember correctly, this depends only on C1 plus C4, which correspond to alpha or beta in blast notation. So do you know roughly how much this one? Because this parameter has been restricted to 10 to minus 5 or something like that.
The branch decay parameter.
Yeah, the new, what's the relation between your new and the copying constant? Oh, okay. I think it's yeah, I think you use actually the Jacobs and Martin's solution, right? Outside.
The exterior problem.
Oh, okay, I see. Okay, yeah, your new equals C1 plus C2. Okay, I see. Okay, thank you. Yeah, yeah, this is exact here. Now, when you take this metric, you already actually use all the freedoms of spherical symmetry. Then you consider static ether. My second question is, what's happening if you consider ether actually always has a radial direction? If I remember correctly, Jacobs and Martin, they actually consider static ether, which means actually ether is always along the t direction. So normally, if you write a metric in this form, you do not have any gate freedom to put the R component of ether as 0. So in a more general case, you should have two components of ether field, T component, R component. So if you consider ether field with R component, you think this will change your result or not? You get my question?
Not really, but I am sure that if, in order to answer this question properly, I think one has to do it. I'm not sure if one can anticipate the answer without actually performing it. Yeah, it would be a good
definitely.
thing.
I think yes, you're right, because also once you consider ether is not static, you have more solutions because the ether field actually will relate the energy condition, then you do not have a Birkhoff theory here. So you have actually more vacuum solutions than in Einstein case.
Yes. No. Yes. There are two things. One thing is that the most general line element, uh, when someone seeks for static spherically symmetric solution, this is the most general line element in all metric theories of gravity. It doesn't matter if you are within GR or within some other modified theory of gravity. Now, Birkhoff's theorem is another thing. You are right that in GR, you know, this theorem guarantees that the Schwarzschild solution is the unique solution. So it doesn't matter if you have a black hole or the sun. But in general, Birkhoff's theorem does not hold in alternative theories of gravity. So one might get the Schwarzschild, the standard, let's say, solution plus other solutions. This is typically what happens in modified theories of gravity. That's true.
Okay.
But
Yeah.
now I'm not sure I understand what am I missing. I'm not sure if I understand what am I missing if I use this metric as such, the standard one, with two unknown functions a and b that depend only on the radial coordinate.
Because in the spherical case, you only have 2 degrees of freedom to choose the metric. Then you already choose the radial coordinate r square, the no diagonal term, the 2 freedom you already use. Then the Isa field in principle has 2 components. So you also impose the 3rd degree of freedom by assuming Isa is static.
I think I understand.
Exactly.
You are saying that in principle here I should put a third unknown function.
Yes, exactly. Normally, yeah.
Yes. And then you let the field equations to tell you that this is r squared. This is what you are saying.
Yeah. Normally it's
Yes,
not.
you are right. Yes, we have started. Yes, we have assumed that this function is r squared right from the start. Yes.
Yeah.
I never
Okay.
thought about that. It's a good point.
Yeah, we can discuss it later. Thank you very much, Gregorius. So, Paris, let's turn to the next speaker. This is actually Dr. Tao Zhu. He's actually on behalf of Lin Kai. So, Tao, you can actually, can you share your screen?
Okay, wait a moment.
Uh-huh.
Okay.
Sometimes use the PDF format is better. Not use
Yeah, I'm
PDF.
using the PDF.
Okay, good.
Yeah, wait a moment. I have a little bit of problem with my. Okay. Can you see my screen?
Oh, yeah. Nice. Okay, very good.
Okay. Good morning, everyone. First of all, I would like to thank the organizer of this meeting and Dr. Andrew Wang for giving me this opportunity to present our recent works. My name is Tao Zhu from Zhejiang University of Technology in China. Since the speaker, Dr. Lin Kai, cannot come, so I will give the talk on behalf of him. In this talk, I'm going to be talking about our recent studies on testing Einstein ether theorem with gravitational waves. Specifically, in this work, we have studied the gravitational waves produced from the inspiral phase of binary and trip systems in Einstein ether theorem. As you can see here, this work is in collaboration with Dr. Andrew Wang, Cao Zhang, Xian Zhao from Baylor University, Dr. Lin Kai from China University of Geosciences, Dr. Wen Zhao from USTC, Dr. Kentayagi from University of Virginia, and Dr. Nicholas Rins from UIUC. Okay. This is just a quick outline of what I'm going to be talking about today. I will first of all give a short summary of the gravitational wave events observed by LIGO, Virgo, and Cargo so far, followed by an introduction of gravitational waves in modified gravities. There will be a detailed look at the properties of the gravitational waves produced from the inspiral phase of binary and trip systems in Einstein ether theory, followed by a summary of our conclusion and future plan. Let's first start with the topics of gravitational waves and their detection. The gravitational wave is a prediction of general relativity. It was first proposed by Poincaré in 1905. About 10 years later, in 1916, Albert Einstein predicted gravitational waves based on his general relativity. In that era, however, the gravitational waves normally is too weak to be observed. The main reason is that the gravitational interaction is the weakest interaction among the 4 fundamental interactions in nature. For example, in order to detect the gravitational waves for a detector with 4 kilometers arms, for example, for LIGO, one must be able to measure the length change of the arms within 10 to minus 19 meter. Such length change is extremely small, even smaller than the radius of a proton. From this fact, one can imagine how difficult to detect the gravitational waves in that era. With the efforts over several decades and the developments of high technology, the LIGO collaboration has made the first direct observation of gravitational waves on Earth. The gravitational wave was detected on September 14, 2015, and was produced by a binary black hole merge. The signal of this event showed the binary black holes consisted of a 36 and a 29 solar masses black holes. The mass of the final black hole after the merge was estimated to be 62 solar masses. The first direct detection of the gravitational wave confirms one of Einstein's predictions, which was predicted nearly 100 years ago. Most importantly, this remarkable discovery opened up a new era of gravitational wave astronomy. This is a great achievement in physics, and this discovery has won the Nobel Prize in Physics in 2017. Since the first event of gravitational waves, the LIGO and Virgo collaborations have already released 52 gravitational wave events, which are detected in the past 3 runs. Most recently, LIGO, Virgo, and Cargo collaboration have announced the 2 new events, GW200105 and GW200115, which most likely are signals from mergers of neutron star and black hole binaries. In this figure, this picture shows all the gravitational waves detected so far by the LIGO, Virgo, and Cargo collaboration. And in the near future, together with the 3rd generation of ground-based detectors such as Cosmic Explorer and Einstein Telescope, and space-based detectors like LISA, Taiji, and Tianqin, we can detect more gravitational waves with improved sensitivities. With current and future improved detectors, the gravitational waves has enabled tests of nature of gravity in a highly dynamical and strange field region. In fact, from the analysis of all the released data of gravitational waves, it is shown that all the current observed events are consistent with the predictions of general relativity. This, on the other hand, also provides opportunity to probe or constrain different modifications of general relativity with current and future observations of gravitational waves. In modified gravities, the gravitational waves can be different from GR in many aspects. In general relativity, gravitational waves only have two tensor polarization modes, while in modified gravities, depending on the series, it can have up to 6 different polarization modes, including 2 scalar modes, 2 vector modes, and 2 tensor modes. Since the modified gravity also modified the Einstein equation, they can also change how the gravitational waves are produced. For example, by binary black holes. After the gravitational waves are generated, both the damping rate and the velocity of gravitational waves during their propagation could be different from that of GR as well. With these mentioned modifications in GWs, how to detect them or make constraints on various modified gravity by using observation data is another important task in the study of modified gravity. In order to test the modified gravities with gravitational waves, we need to study in detail how the properties of gravitational waves can be different from those in GR. Actually, in this direction, our group has been working in tests of different modified gravities with gravitational waves from batteries, including the gravitational waves produced in the spiral phase in different series of gravity, the waveform of GWs in parity violating gravities and their constraints by observations, and the quantum modes of black holes in modified series of gravity. Because of the time limitation in the following, I will only present our recent works on gravitational waves generated in the spiral phase in Einstein-Issa series. For gravitational waves generated by a compact binary systems or triple systems, the process of gravitational radiation can be divided into 3 different phases, as you can see from this figure: the inspiral phase, the merge phase, and the random phase. In this talk, I will only focus on the gravitational waves emitted from the inspiral phase of the binary or triple systems. Okay, let's go to the second section about how to calculate the gravitational waves from the inspiral phase in a modified server of gravity and their properties in Einstein-Issa server. Actually, as I have mentioned, gravitational waves in modified gravity can be different from GR in many aspects. Different modified gravities can have different predictions. There are also a large number of modified servers of gravity. Choosing a server to work with is normally a personal taste. Here, we chose a server that satisfied the following rules. First of all, the server is self-consistent. That means it should be free of instability, ghosts, and the corresponding Cauchy problem is well posed. Second, it should be consistent with all observations and the experiments carried out so far. And at last, it can provide new predictions that can be tested in the near future. Once we have a proper server of gravity, we then apply a general procedure to perform the calculations of gravitational waves emitted from the spiral phase. We first of all, we divided the space-time into two different zones, the near zone and the far zone. And then we solved the field equations in each zone. In the far zone, we can use in the weak field approximations. And then we need to connect the solutions in both zones. With the solutions in the far zone and near zone, we then can perform the calculations of different polarization modes of gravitational waves and their waveform. As we have mentioned, in modified gravities, gravitational waves can have 6 different polarization modes, as you can see from this figure. In GR, we only have 2 polarization modes. But in principle, in modified gravities, we may have up to 6 different polarization modes. In order to test modified gravities, we also need to calculate the response fraction of different detectors and parameterize the corrections to GR by the parameterized Einstein approximations. Because of time limitation, I will not go into details of how we perform the above procedure in Einstein ether server, but only report our main results here. The Einstein ether server is the vector tensor server of gravity. In addition to the Einstein-Hilbert action in GR, this server introduced a unit and time-like vector field, the ether field. Because of the presence of the ether field, the servo can have 3 different species of gravitons, the spin 2, spin 1, and spin 0. Because the ether field is time-like, so it defines a preferred time direction in the space-time. Because of this preferred time direction, the Lorentz symmetry of the servo is violated. So this is one of remarkable features of this servo. On the other hand, this servo is also self-consistent, and its Cauchy problems is well posed. Recently, it is also shown that this servo is consistent with all experiments and observations carried out so far. As you can see from this paper, we can impose the servo constraints on the coupling constant of the Einstein ether servo. Actually, the gravitational waves radiated from the Bernoulli systems has been also studied by using the post-Newtonian approximation. Recently, our group has revisited this study with newly allowed parameter space by first calculating the gravitational radiation of M-body problems. In the following slides, I will report our main results of our study. First of all, we calculated all the 6 polarization modes of gravitational wave explicitly. That includes 2 tensor modes, 2 vector modes, and 2 scalar modes. And we find that the 2 scalar modes, the base mode and the longitudinal mode, are always proportional to each other. Actually, this is not a surprise. Since the Einstein ether servo can only have 5 degrees of freedom, this implies it can only have 5 independent modes. Because of the presence of the 4 additional polarization modes, the radiation powers of a given system in Einstein ether servo in general are quite different from that of GR. As you can see from these expressions, the coefficients A, B, and C are functions of the coupling constant Ci, C1, C2, C3, and C4. From this expression, one observes that the coefficient A is different from that of GR, and the terms with B and C are new contributions from the Einstein ether server. So it's quite different from that of GR. Recently, we have also applied these expressions to the triple systems. This is the first observed relativistic triple systems PSRJ0337 plus 1715. For these systems, we find that the dipole radiation is as large as the quantable radiation, can be as large as the quantable radiation. Actually, this is very different from that of GR. Therefore, it would be very interesting to look for gravitational waves emitted by the trip systems. This may provide a way to test the Einstein ether server with observations of gravitational waves from the trip system in the future. We also considered the gravitational waves emitted from the neutron star black hole binary. A few days ago, LIGO, Virgo, and Cargo has announced 2 new events, which most likely are signals from mergers of a neutron star and a black hole. These events imply such as binary systems are common in the universe. By applying our general expressions to such systems, we find that different polarization modes of gravitational waves can be written in these forms. So we write the gravitational waves in a form of here A plus A cross is the amplitude of the gravitational waves, and theta is the theta and 2 times theta are phases of the gravitational waves.
So you have 5 minutes left.
Okay, I will finish it quickly. Okay, we find that different polarization modes of gravitational waves can be very different from that of GR. It is easy to say that actually here we have 2 principal modes, theta and 2 times theta, which is different from GR. And as you can see, this figure shows the time evolution of the amplitudes of different polarization modes. As you can see from this figure, the scalar mode HB and HL are suppressed relative to the tensors by a factor of 10 to 3. This implies that it will be extremely small. It will be extremely difficult for GW detectors to measure these actual modes directly. However, from the first figure, it is shown that the tensor modes can also be very different from that of GR. By using this factor, we may could the Einstein ether server can be constrained with the observation of gravitational waves in the future. And due to the additional polarizations, the orbital angle frequency is also different from that of GR. So as you can see from this figure, the frequency, the changes of the growing of the frequency is more repeated than that of GR because we have additional radiation, the radiation of the scalar mode and vector mode. Therefore, with more and more gravitational wave events being observed and the continued improvement of the sensitivity of detectors, gravitational wave astronomy will provide important constraints on the server. Now it's time to make some conclusion and outlook for future plan. The conclusion can be summarized by the following points. First, we calculated the waveforms polarizations, response functions, or gravitational waves emitted from binary and triple systems in Einstein thesis theory. Second, as we have shown in some cases, the properties of gravitational waves can be sharply different from those in GR. Therefore, current or future observations can be used to place constraints on the theory. Since we only consider the gravitational waves emitted from the spiral phase, it is also interesting to extend our studies here to the merge and ring-down phases. Actually, we have already carried out some studies of gravitational waves emitted during the ring-down phase in several modified gravities. For example, the scalar Einstein Gauss-Ballistic theory, Einstein ether theory, and the parity violating scalar tensor theories. So in conclusion, the area of gravitational wave autonomy has just started, and there are many surprises are waiting for our discovery. That's all I would like to present today. Thank you very much for your attention.
Thank you very much, Tom. Any question, please?
Yes, I have a comment actually.
Oh yeah, go ahead, Judge.
Okay.
If you use the condition of hypersurface orthogonality, you can make the Einstein theory equivalent to non-projectable Horava theory. And in that case, you subprime some extra degrees of freedom, but you have this one extra degrees of freedom. But if you also impose a condition in the space of parameter, you also can subprime the extra degrees of freedom, and you get exactly the same degrees of general relativity. The condition is equivalent to the condition I showed in my presentation of with the name of critical case. I don't know if you know that. So I think it could be interesting to think that there are some restrictions or some special kinds in which you can reduce and also get exactly the same number of degrees of freedom of general relativity. That's the comment.
Okay, thank you very much. Yes.
I think that's very good observation, George. This actually talks, George just said, because if you choose lambda equal 1 over d, d is a special dimension, then you just limit another actually freedom. So the degree of freedom will reduce to Einstein theory. So in that case, you can see what's happening for the gravitational radiation. But quickly answer this actually shooting pair, there still be a difference, Joe. The difference is not because of the different extra channel of radiation, just because the theory is different. Mathematically, the field equation are different. Okay, I think Paris, thank you, Tom. Again, it's time for
Yeah, thank you.
Yeah, to go to next. Yeah.
Okay.
Jim, can you hear me? Dr. Jim Cole, please.
Okay, that's me. Sorry, I didn't.
Sorry, yeah. Yeah, this is your turn.
Yeah,
Go
sure.
ahead.
Just hang on. So let me just put this presentation. All right. There you go. Can everybody see my presentation?
Yes.
Great. So shall I start?
Yeah, please go ahead.
Okay. So good afternoon, everyone. My name is Jan Kwapisz, and I would like to present my work, which is a joint work with Jan Chojnacki, who will actually speak after me about another aspect of our work. And first of all, I would like to thank the organizers for having me here and for inviting me to give this talk. So let me, after this brief introduction, let me start. So the thing that we will discuss is so-called finite action principle, which was put into in 1980s. Roughly, the idea is that when we are discussing some system that evolves on a quantum level, then the relevant then we have to sum over all the possible field in the path integral. However, much of the sum will cut out, and what John Barrow and Tipler proposed is that actually what will happen is when we do this sum, then only the bits with the action that is finite will survive. This is very apparent in after performing a weak rotation. So, for example, in a non-gravitational system, because then we have the damping factor minus s, and if action is infinite, then one indeed can see that this is infinitely damped, this configuration, and hence don't contribute to the path integral. In the Lorentzian case, it's this argument that actually goes back to Feynman, that when you have various paths that are that have this infinite action, and then around them we will have a cancellation of different due to fast oscillations. We would have a cancellation of that contributions. So we would explore what this finite action principle can give us for black holes, in particular for Horava-Lifshitz theory. We would be interested in applying it for singular and non-singular black holes. So what we would be interested in is whether, because we know that quantum gravity is supposed to resolve the singularities problem, so we would ask whether there exists theories such that the action of a singular black hole would be infinite, while the action of a regular black hole would be finite. Then such a theory can resolve the issue of singularities via this finite action principle. This has been put out in this reference, this way of thinking. Okay, so let me start. So quite interesting is that when we add to Einstein-Hilbert term, we add this higher curvature constraints like y squared or r squared, then we get interesting phenomenology for cosmological as well as for black hole spacetimes. However, this theory, as you might know, is plagued with, even though it's renormalizable, and it's actually asymptotically free. However, it has a ghost, which can be resolved in various ways. One is the new degrees of freedom. The other one is infinitely many derivatives. So we add infinitely many so-called non-local gravity. The other thing is that maybe there is some non-perturbative mechanism in this theory that will restore unitarity. And finally, what we can do, we can break Lorentz invariance, and that would be our choice. And if we break Lorentz invariance, then we land in the Horava-Lifshitz framework. So what is Horava-Lifshitz? Theory It's a theory where we break Lorentz invariance to foliation-preserving diffeomorphisms. So we break to such that we have diffeomorphisms of this type, so reparametrization of time, and the spatial ones on a Cauchy surface. Horava-Lifshitz is often spelled out in terms of ADM formalism, which is convenient to analyze this foliation diffeomorphisms, and the action is given roughly like this, where these are the kinetic terms, while this is the potential term. The GR is installed in the IR limit of lambda going to 1/3, and this potential term will in general for various Horava-Lifshitz theories can have terms up to r to the third due to renormalizability conditions. However, actually what we will find out is that this will give the same conditions in terms of black holes as just the r squared, but r squared, I mean r, the spatial r, so the three-dimensional r. And this comes, and we will see that this is indeed so. Let me just mention that the various theories of the various Horava-Lifshitz theories, the projectable one, non-projectable one, the ones with up to r squared, up to r cubed, up to r squared, etc., with additional symmetries, but that would be highly irrelevant. So what we would need is just this structure plus potential in which we will have r and r squared and some combinations of Ricci tensors that are contracted with each other. That would be all we need. So I wouldn't go into details of various Horava-Lifshitz theories and their constructions. What we would like to do is taking a space-time, for example, some black hole space-time, and we would like to calculate this from with various radiuses, because since we are discussing black holes, then the radial coordinate is the most relevant one for us, and all other integrations are in a sense implicit, so I didn't put them here. And we choose RIR such that there are no IR divergences, for example, from cosmological horizons. And what we do, we require this action to be finite as we approach R UV to 0 for regular black holes, and we require this one to be infinite as we approach the same limit for singular black holes. There's one subtlety for Horava-Lifshitz that one has to mention, is that in particular in Horava-Lifshitz theory, various for Einstein gravity, the singularities that are coordinate singularities can become essential singularities for Horava-Lifshitz. This is, for example, the case for a horizon of the Schwarzschild in Horava-Lifshitz. So that could be a subtlety, but however, this does not play much of a role in our investigation. So let me start with singular black holes. I would take the Zeta Schwarzschild, which is in generally given like this, with this choice of parameters. One can check out that this is just a funny choice of coordinate system. And what we get for this solution is that R, the spatial R is equal to 0, K is equal to this. Hence, if I would integrate this, then I will get for lambda non-equal 0, I will get that there are divergences as I approach R UV to be 0 or RS to be this. This is the cosmological horizon, so we are not really interested in that. However, this is the essential singularity. Let me remind you that for Einstein gravity, we'll get action that is finite. We'll actually get action that is zero because Ricci scalar does vanish for this metric. So let me just remind you about that. While here we get an action that is divergent for due to this kinetic term. However, now I can change the frame to the orthogonal frame, which is not a solution in Horava gravity. However, again, we are discussing path integrals, so in a sense, every metric goes. So not only solutions of a theory can go into the path integrals, also the metrics that are not solutions. So now one can repeat the same quite straightforward calculation, just calculate the invariance, and now one would get that this term is divergent. So there's two different Schwarzschild solutions in Horava-Lifshitz. Both will have infinite action. Now we're to the regular black holes. In particular, we have, here I will discuss Hayward metric, which is a regular black hole solution in GR. Let me mention that there are non-regular black hole solutions in Horava-Lifshitz found so far, best to my knowledge. And now let us repeat the same analysis. We calculate the invariance, and now we see that, as one can already see that it seems to be okay. And if I now integrate those, then I will get finite results, which can be seen from the fact that here I have this additional g to the third term. If I will drop this, then I will presumably get the non-zero. Then I would get the non-zero, since this would be 1 over r to the 6, which cannot be dealt with. And hence the action is finite. Same can be done for Dymnikova spacetime and other spacetimes of this thing. And here is, in a sense, an interesting challenge would be to find this Horava-Lifshitz regular black hole and to check whether this action is finite. However, as far as I know, this is still work in progress within some groups working on Horava-Lifshitz. Finally, let me mention wormholes. If wormhole are a similar solution to a black hole, only that up to this ring, we call it our universe. This is a throat, and this thing inside we call the other universe. So we have this wormhole thingy that connects different patches of our universe. In particular, we have here we chose this, so we have to integrate only up to m, because this is our universe. In particular, I chose some exponential metric for wormhole, and for Horava-Lifshitz, I get the invariants, which are those, and if I would integrate them due to this damping factor here, I would get the results that are finite again, which can lead to some conclusion that actually wormholes are from the point of view of finite action, are on the same footing as regular black holes, or for Horava-Lifshitz, they are even more preferred, because we know Horava-Lifshitz wormholes, but we don't know any regular black hole solutions in Horava-Lifshitz. So there might be actually that from the point of view of this principle, wormholes might be preferred over a black hole for Horava-Lifshitz. However, this is under this assumption that there's no regular black hole solutions in Horava-Lifshitz.
You have 5 minutes left.
Yeah, I'm finishing. So to conclude, quantum gravity shall resolve the singularities, both cosmological and the black hole ones. To do so, the finite action principle has been proposed, which selects what can be in this exponent here. In particular, Horava-Lifshitz gravity satisfies this principle And as I have mentioned a couple of times, in a sense, this is Horava-Lifshitz session, so maybe somebody would be interested in finding this regular black hole. So this is, in a sense, some kind of a challenge to give to the community, that there are no regular solutions, and hence there's this black hole wormhole trade-off. There are also very interesting consequences for cosmology based on that principle discussed, for example, in these papers, and also they will be discussed in the next talk by Jan Chojnacki. And with that, I would like to thank you for your attention.
Thank you, Jim. Any question, please?
Yes, I have a question.
Yeah, go ahead.
Yeah.
In the case of the wormholes and the known solutions in Horava theory, with or without cosmological constant, the wormholes has a singularity, an asymptotic singularity. So I was wondering, is this is important for your analysis or not?
As I have said, we cut off the we cut off the IR singularities. Let me say that this is a little longer issue to discuss, but generally speaking, we are interested in a sense a local. So what happens in or around the black hole or wormhole, not what happens in the asymptotic regions. Same for cosmological horizons. This comes from the fact that actually, if one discuss the path integral, what one is actually interested as the transition amplitudes, and these, in a sense, know only about this local patches, not about this what happens in the whole universe. So this comes under the name finite amplitudes principle now, but I didn't want to discuss it because it's a pretty new thing. So
okay, so.
Yeah, let me put it that way. I hope that answers your question.
Yes, okay, I see.
Yeah.
Any other questions?
So all of this, like cosmological horizons, etc., will play far bigger part in cosmology, for example.
Well, but the wormhole is an astrophysical solution. It's when you speak about the asymptotic region and a black hole, it's part of astrophysics. But I understand your point. But I think one thing is cosmology, and another thing is a source, and an isolated source with an exterior. But I understand you are interested only in some region of the space, many of the throat.
Yes.
Okay.
Okay. Thank you, Jim. I think perhaps let's turn to the next speaker. The collaborator of Dr. Jim Chojnacki. Is this spelling correct?
It's Jan with.
Okay, go ahead, please.
Okay, so let me share my screen. Okay, great. Can you see it?
Yes, I can see.
Great, wonderful. So thank you very much for the opportunity to talk to you today. I would like to briefly elaborate on the cosmological predictions from the talk of Jan, who told you a lot about black holes and wormholes. And I will focus mostly on the Big Bang in Horava-Lifshitz theory. Okay, so a quick setting of common background. This whole principle of finite action principle is based on the idea that in the gravitational path integral, the probability amplitudes are weighted with this exponential factor. And in the case of Euclidean signature, we will have just minus action. So going with infinity, this will be very, very strongly damped. And in the case of Minkowski signature, we somehow propose that there will be a similar damping, however, due to destructive interference of neighboring field configurations. And this is exactly what Barrow and Tipler were motivated by when formulating the finite action principle, that field configurations with infinite classical action do not contribute to the path integral and do not contribute to probability amplitudes. And so far, there has been a lot of cosmological predictions stemming from quadratic gravity, from this Lagrangian that Jan showed you previously. And for example, 2 years ago, Lanier and Stell showed that the Big Bang of quadratic gravity, based on finite action principle, was necessarily homogeneous and isotropic. So all of the anisotropies and inhomogeneities were dynamically excluded from the probability amplitudes. Moreover, such universe would be accelerating, which is a nice thing to have in your universe. Okay, and what I would like to Jan told you about wormholes and black holes. I would like to go with it further and see what predictions are there for Big Bang from finite action principle in a unitary case of Horava-Lifshitz gravity. So when we are ghost-free and we don't have these pathologies of usual quadratic gravity. And by pathologies, I mean just a ghost degree of freedom. When we include quadratic gravity term due to Ostrogradsky's theorem, we will have this this massive particle which has a wrong sign of kinetic energy. And we know that it will always happen when we have, for example, quantic time derivatives, as here. One way to get rid of it is, well, the whole panel is devoted to it, is Horava-Lifshitz gravity, which is based on ADM decomposition. And then we construct tensors, which are tensors with respect to foliation preserving diffeomorphism. And from these tensors, we can construct Lagrangians. So we will use spatial Ricci curvature, extrinsic curvature, this I vector, and covariant derivative with respect to spatial part of the metric. Then the Lagrangian may be divided into classified into two main groups, into kinetic terms, which look like that, and numerous potential terms, which are just contractions of all the tensors that we have. And at order 6, there are more than 100 of such scalars. So we need additional symmetries to restrict their number. And this is what Jan mentioned. So we can impose parity, we can impose projectability or detailed balance. And with this assumption, we get Horava's minimal theory, which consists of the usual Einstein-Hilbert action and second order gravity and the third order curvature truncations. All these scalars are with respect to the spatial metric. Okay, so now the question is whether the cosmological predictions from finite action will hold for this ghost-free theory. In particular, whether the universe has isotropic, homogeneous, and flat and accelerating beginning. This is important because it somehow gives us an alternative to inflation. It chooses dynamically a preferred state, initial state of the universe. And I would like to show you on the case, in the case of anisotropies, that it is the case with some caveats, which I will discuss later. So we'll be interested in a limit of time going to 0. So instead of black hole singularities with R going to 0, we will approach the Big Bang singularity. And we consider a model example of an anisotropic metric, which is Bianchi-9 spacetime, which has this one forms, which are Bianchi-1 forms. They are introduced so that the metric is diagonal, and they also satisfy this relation, which gives a very simple expression for Christoffel symbols, which are just proportional to this epsilon ijk. Okay, and this spacetime, I could give you explicit form of omega I and omega j. However, they are not very enlightening. What is important to know in our case is that when we choose these functions of time, m, q, and r to be equal, then we will recover the usual positively curved Friedmann-Lamid-Robertson-Walker. Okay, so we proceed with this knowledge and we assume, we put an ansatz that while approaching Big Bang, these functions are in a power law manner with different exponents, which are real. Okay, so if the exponents are exactly the same, then we will have the usual isotropic expansion of the universe. And on the next slide, I will try to convince you that it can't be the case. So, okay, yeah, let me proceed. Okay, so we may calculate this, all of the curvature scalars in the minimal theory for this Bianchi-9 metric. It has been done in 2017, and they have this form. So now we should check for every single term whether the limit of t going to 0 is regular or not. And for example, if we consider term proportional to this m to the 4th, we will see that it will be of this shape. And the exponent, in the case, if the exponent is equal to -1, then we will have a logarithmic divergence while going with t to 0. So we impose that the exponent must be bigger than 1. And this needs to be done for each of the terms, and we will have a very large set of inequalities with 3 variables, which are m, q, and r. Okay, so now we should check whether they are somehow contradictory. And if they are, this means that this anisotropic spacetime has infinite action. And since it has infinite action, that it will be dynamically excluded from the path integral. And it so happens that indeed it has a contradictory set of inequalities. So anisotropic spacetimes are excluded at the beginning of the universe. However, it also happens that the isotropic case of positively curved Friedmann-Lamid-Robertson-Walker is also leads to an infinite action. And there are a few ways to deal with this. First of all, is we can verify that it can be checked that the flat case of FLRW W has finite action in Horava-Lifshitz theory. So our initial state of universe might have been homogeneous, isotropic, and flat. But there are also other ways to bypass this problem of infinite action. One may give up Big Bang, which is a big statement. However, there exist alternative oscillatory solutions which have bounded value of A between some minimal and maximal value. And one may also get rid of the cubic terms. So let go of the minimal theory and consider something else, because the cubic terms are responsible for contradictions in this set of inequalities. All right. And that's most what I wanted to talk to you. To conclude, only finite action fields configurations contribute to path integral. This is the finite action principle. In the case of usual quadratic gravity, we will get a homogeneous, isotropic, and flat universe when going to the Big Bang, and also resolve the black hole singularity problem. But there is this problem of ghosts, which we deal with by introducing Horava-Lifshitz framework. And then we will see that our conclusions from quadratic gravity are partially also applicable as the beginning state, the initial state of the universe is allowed to be a homogeneous, isotropic, flat Robertson-Walker metric. But if we want to have some curvature, then we need to deal with it in another manner. For example, by letting go of the minimal theory and considering only lower scalar order of curvature scalar theories and oscillatory solutions. Okay, thank you very much.
Okay, thank you, Jim. So any question, please, to Jim? Okay. So I have a quick question. No, this is actually to both of you. You use actually finite action. So this will avoid all the so-called the scalar singularity. For example, in Einstein theory, we divide the space-time singularity into scalar and no scalar one. One example is if you consider a plane gravitational wave, all the 14 scalars are 0. So then the action should be finite. But we do have actually no scalar singularity, which is physical. In that case, actually, how do you exclude those kind of singularities?
So my understanding is that we consider scalar singularities because they are the things that appear in the gravitational path integral, which is supposed to be that theory of gravity, of quantum gravity. So my understanding would be that from some other principle or some other considerations, gravitational path integral approach will get rid of these physical singularities in the measurable quantities. Yeah, so, so this is like first step to get rid of the all singularities in the gravitational theories.
So,
okay, thank you. Any other question?
One could consider that only those transition amplitudes would be okay, which have a finite probability, for example, but let me say that this is not very investigated yet.
Okay, thank you. Any other questions? If no, I think perhaps we can do the following. First, we actually, you can unmute all your microphone. We thank all the speakers today, the 8 speakers. After that, perhaps we can have a further discussion over all the talks. So let's first give a pause to all the actually 8 speakers, please. Yeah. Thank you. Yeah. Okay. Now I think perhaps so open time. It's time actually for open question to all the speakers or any of us. So we just free talk. But this is normally the meeting, the local organized community only give us about 15 minutes. So we will stop whenever they just shut off our line. So please feel free to ask any question.
Dr. Wang, I have a question about.
Okay, yeah, go ahead, Satish.
After all these observational results and everything, right? So currently, what model, what theory of Horava-Lifshitz is the best to work with, which has survived all these tests so far?
That's a good question. I think if you consider, let's say, because Horava-Lifshitz theory is has high order term. If you consider the observations only perhaps the low dimensional term has a major contributions, which means perhaps you reduce to the actually chronometric theory for the non-projectability case. There actually you can use, for example, gravitational waves or the observation black holes to put a constraint on the free parameters. So in the chronometric theory, there are only three free parameters, which correspond to C14, C1 for C13, and C2. C13 is equal to C1 plus C3, C14 equals C1 plus C4. So then you can actually see the constraints. I think there's some work recently using the observation gravitational waves GW 170817. This is from binary neutron stars. I forget exactly the range of constraints, but you do actually have some thermal constraints from the velocity of gravitational wave, spin to particles, spin to gravity.
So the chronometric theory is the best option as of now.
You have to be careful. Horava-Lifshitz theory has actually several versions. For the projectability case, there are always instability in the infrared.
Yes. So projectability is ruled out, right? So detailed balance, no more detailed balance, no more projectability. So it's better to work with the non-projectable case.
Projectability, if you see that actually, that means you use instability rule out. But on the other hand, projectability is normalizable. This has been just proved, like judges show. But no projectability case, we do not know if the series quantized. I think George perhaps has more to say about the non-projectability case about quantization. George, do you have any comment about the quantization of a non-projectability case?
Yes, but one thing that it is difficult to prove the normalization, but it doesn't mean that it is not normalizable. I think most of people think that the Horava theory, projectable and non-projectable, are normalizable. But the difficult part is to prove it explicitly. So I think at the end is just an attack to define correctly the quantization, to incorporate the measure correctly, and to analyze step by step the cancellation or the divergence in diagrams. But it is a task that has to be done. But I think many people are confident about at the end the theory is renormalizable because the high order curvature tends. But this is difficult to prove it, especially because many people is used to tend to use the gauge theory, the techniques of gauge theory, And the non-projectable is not exactly a gauge theory because of the presence of the second class constraints.
Okay.
In any
thank you.
case, about the question of the phenomenology, it is important to think that the restriction affect the coupling constant of the large distance term, the Z equal 1 terms. So probably in the non-projectable case, you have to adjust the value of this constant to the relativistic values, alpha 0, beta 1. So this is another problem. You can prove the renormalization, but how do you ensure that coupling constant remain in the relativistic? The coupling constant of the lower energy terms remains in the relativistic values. But on the other hand, phenomenological observation probably do not affect the coupling constant of the higher order terms.
Mhm. So just to follow this question, what about the projectability case with the U1 symmetries? If you impose a U1 symmetry in the projectable case, you think the theory can be still renormalizable, or your analysis we can show easily renormalization?
Probably yes, no, because at the end it is a matter of the power of the higher order terms.
Mm-hmm.
I don't know, but I think yes, the answer could be yes.
Yeah, this actually also Satish related to your question. If in the projectable case, if you impose U1 symmetries, then the infrared, the instability disappear. So the theory is okay.
That's good.
Yeah. Okay. Susan, I have a quick question to you. Actually, I didn't get a time to ask you. Can you hear me? Susan? I think he's still here. Susan, can you hear me? Oh, okay. So perhaps, yeah. Anyway, so this actually, do you have any other questions, Satish?
That's all, actually. It was good to see Tal too.
Yeah.
I wanted to ask
Susan,
him.
are you still there? Oh, perhaps he is not. Yeah. Okay. Anyway, so I still see that.
I have a question for Lisa.
Okay. Lisa, she actually sees the gun or not?
Oh, sorry.
So she's a gun. Yeah. However, you can send an email to her.
Okay.
Yeah. George, what about the let's say now you consider 2+1 in a non-projectable case, then you have 0 degree. So if you go to actually 3+1, this will be more complicated, definitely, right? For the non-projectable case.
Sorry, the non-projectable.
Now you consider actually 2+1 case, the renormalization for 2+1. What about 3+1 case?
Well, you have still 1 degree of freedom in 2+1.
Yeah.
And the difficulty is probably the same as the 3+1, because you also have second-class constraints in the non-projectable case. So I think it makes no difference in the 2+1 case.
I see.
Except the case of the critical case when lambda is equal to 1 over the dimension when you don't have any local degrees of freedom. But in the generic case, you have 1 degree of freedom in the non-projectable case.
Okay. Yeah, because I think in the projectability case, they first show the renormability in 2+1. Then they say, okay, their result actually can be extended to high dimension. So my question was exactly, can you do the same generalization from 2+1 of a no projectable case to 3+1? So yeah, I think your answer is good in the sense.
Well, you first have to prove
the second case.
You first have to prove the 2+1 case, and this has not been done to prove the normalization in 2+1 case.
I see.
And if it works, probably the same extension works. Like they do in the 3+1 case.
Okay. Yeah. Thank you. Susan, are you still there? Okay, can you hear me? I think he cannot hear us. Anyway, so perhaps we can stop here if you guys do not have any questions. Nice to talk with you, George. I think we never meet each other, but I know your work you have been working on Java theory for many years. It's good to continue work on this. Yeah. Satish, do you know George personally? Do you guys
No,
know each other?
I don't.
Okay. Yeah. George Satish was my former PhD student. Now he got a position in Rio, the Federal University of Rio.
Where does George work?
Yeah.
George
Nice.
actually working in Chile.
Oh, okay.
Yes, yes.
Okay. Close to
So
me
you're a neighbor.
than to you.
Yeah.
In the northern part of Chile, in the desert of Atacama, the driest desert of the world.
I've never been to Chile. I would very much would like to. So once the pandemic is over, I think I'll be free to move around, right? So maybe I will meet you in Chile sometime.
Yeah.
Yes.
Chile is a beautiful place.
Yes, but
Yes.
the northern part is very different to the south part. Many people think the south with drains and lakes, but the north part is a desert.
What is the name of your institution? Is it the same as the one
Antofagasta.
the Janelli is?
And Universidad de Antofagasta.
Okay. I think there was recently I saw maybe 2 years ago some quantum gravity school in Chile, some institute. I don't know which institute is that.
Probably in Santiago, in the capital.
Santiago, I think yes, in Santiago. So how far is your place from Santiago?
It's far because Chile is large.
Oh yes, it's very long, right?
Yes, by plane is like almost 2 hours.
Oh, okay.
Oh,
That's
really?
long.
Oh, that's really long. 2 hours for Chile.
Yes, it's a very strange geography. It's large.
Yeah, it's like a line. The whole country is near, on the coast.
Yes.
Yes.
Yeah.
I think
So-
Chile, the corona problem is less in Chile than it's in Brazil, right?
Well, Brazil is a very special case to compare with. Yes, but we have a problem also with the pandemic. The vaccination is good, but still we have a lot of cases, and hospitals are very charged with cases.
Okay.
So it's better than Brazil, but situation is not okay in Chile.
Okay.
Now it's publicly, it's the restaurant shops are open or are still closed. The restaurants.
Restaurants are open, but with restrictions.
Okay.
Some people, just a few people can enter in, and so on. The university is closed. We have we are working on home, but the rest of the city have more or less normal activity.
That's the difference, right? So in Brazil, universities are closed, but all the restaurants and bars are full.
That's true.
Yeah, I think in Brazil, the bars cannot be closed. What about the vaccination in Chile?
It's good. It's good. It's one of the best words with vaccination, but in the world. But still, there is a lot of cases of illness with the pandemic. But vaccination is good. A lot of people have been vaccinated.
Yeah, that's very good. I think now seems, especially in the US, you can see the place with a less percentage of vaccinations have actually high risks, have more actually infection cases. Vaccination seems very important.
That one, how are things in Waco? Are things back to normal? Because no more social distancing in the US now, right?
Yeah, no more. The university, Beta actually plan to have all the classes in person next. This is the fall semester. So I think that people are not forced to take a vaccine, but if anybody wants to take, they can take immediately. There's no line. There's a good place, even shopping. In some acres, Walmart, there's a place you can take a vaccine. But I'm not so really understanding. Still, there are lots of people who do not take.
Yes, they would rather die than take vaccine.
So I could not understand this. Even some people still use a slogan against the vaccination.
Yes. This is just the nature way of eliminating some population. So.
That's true. Okay, I think let's talk with you, George, and Satish. Satish, your family are okay, right?
Yes, we are good. We are good.
How's the girl?
She's good. She's good. She can talk a lot.
Okay, I see. No, she's more than
the next time when you come, she will be speaking a lot.
Okay. George, you know, Satish's daughter, the name is called Gravity. I think a few people.